Okay, thanks. Let me start by thanking the organizers for putting together such a nice workshop. Um, Today's talk is based on a paper that appeared earlier this year, and it was done in collaboration with Luca Griguolo, Jacopo Papalini, Domenico Seminara, and Itamar Yakov. So this work deals with a theory that has been studied for many decades now, and actually not just studied, but the theory was solved essentially 50 years ago by Migdal. So it might be surprising that there are some basic aspects of the theory that, the questions about the theory that remained unanswered for such a long time. So I will start by introducing the theory. So the first part will be maybe for some of you quite basic, but I don't want to assume any prior knowledge of the specific of Yang-Mills theory in 2 dimensions. So the theory is defined by the usual action that you always have for pure Yang-Mills theory. Where you write it in terms of the curvature of some gauge connection A. And the action is, of course, well, gauge invariant. And I will mostly consider SUN an SUN gauge group. That's why to keep the notation a bit less cumbersome, I'm not I'm expliciting that here the inner product in the Lie algebra of the gauge group G is just given by the trace in the fundamental representation. And a special feature of 2 dimensions is that the theory is invariant under a large group of space-time symmetries, which they go under the name of area-preserving diffeomorphisms, which make the theory depend on very mildly on the background geometry, because essentially it will depend on the geometry only through the only invariant that you can construct out of the volume form, which is the total area of your surface sigma. And also, well, then you would expect that, okay, you have 2 couplings then. You have one is the gauge coupling epsilon, and one is this area rho, but they really always appear together in the combination in the product, so epsilon times rho. So you can just set rho to 1 and only deal with one adimensional coupling, which is epsilon. So, well, epsilon is not adimensional, but if you multiply it together with rho, you get something adimensional. Now, if you're interested in the classical theory, then you can study the critical points of the action, and these are just the solutions of the Yang-Mills equation, like in any dimension. But the theory also admits another formulation, which is through some supersymmetric version of a BF-type theory, where you introduce auxiliary fields that takes values in the Lie algebra of the gauge group. One is a scalar phi, and the other one is a 1 form, psi, which is Grassmann odd. So it is like a fermionic degree of freedom. And the advantage of writing it in this way is that you get supersymmetry for free, essentially, because the theory now has some fermionic symmetry generated by this fermionic charge Q. Of course, these are auxiliary fields, so if you integrate out all the auxiliary fields, you land back on the original action. Now, there are various ways that you can go about to quantize this theory. And I want to look at 3 ways, because this will be important for what's gonna come next. So the first one, and this might be, if you're not already familiar with this might be a bit surprising, that one way to study the theory in the continuum is to start from a lattice formulation. So you pick your surface sigma and you start triangulating it. And then you do the same thing that you always do when you have a lattice theory. So you have a discrete theory where your degree of freedom that live on the edges on your lattice. These are degrees of freedom that takes values in the Lie group G. And they correspond simply to parallel transport of some putative connection along the edge. Now, you can consider for each plaquette, elementary plaquette P, you can consider the holonomy, which is obtained simply by taking the product of this degree of freedom along the edges. And And then you can stitch together, you can construct the partition function by stitching together this plaquette's contribution just by integrating over the degrees of freedom. And each plaquette contributes with this specific factor, gamma of p, that is obtained by summing over irreducible representations of your gauge group. Now, here you have the dimension of the representation, an exponential in which you have the quadratic Casimir of your representation that acts as a Hamiltonian. And here you're looking at the character of the holonomy around the plaquette, a character computed in this specific irreducible representation R. And the reason why characters appear is, of course, you want gauge invariant degrees of freedom, so these, they provide a basis for class functions of elements of the group. Okay, so why is the lattice formulation important and special in 2 dimension? Is because it's easy to prove that if you refine your lattice by introducing more edges, more vertices, and so on, you will get always the same result. No matter how coarse or fine your lattice is, the result is always the same. So you can think that taking the continuum limit is absolutely trivial. You compute the partition function with any triangulation of your surface, and that is the result that you would get in a continuum. This, what, sorry, what? Rho is simply the area of the plaquette. Yeah. And the result, by stitching together all your plaquette contribution, is something that is sensitive, again, as I said, only in terms of the total area of your surface that comes from summing the area of all the plaquettes, and knows about the topology only through this power here. You raise the dimension of your representation to the Euler characteristic of the surface that you're studying. So this gives a fairly like combinatorial group theoretical version of your action. So you're writing the result in a way that is combinatorial in nature. But of course, there are other ways of, and this was done already in the 70s by Migdal and then revisited by Witten in the early 90s. But that's the full result for the partition function. And you can also use the same approach to compute observables like Wilson loop correlators or things like this. This is a lattice formulation, but another formulation is something that you always have in your toolbox when you're studying local quantum field theories that have a Lagrangian formulation. You can do it through a perturbative expansion in the coupling. Here we have a gauge coupling. Now the price that you're paying, of course, because you're working with local degrees of freedom is that they're not gauge invariant. So this involves some gauge fixing that we all know and love. You introduce BRST ghosts and anti-ghosts and a new term in the action. But perturbatively, the theory is not too bad because it's super normalizable. The gauge coupling has a dimension of a mass square because we are in 2 dimensions. So there are no divergences that come from the gauge degree of freedom, but you do have divergences that come from the fact that you're coupling your theory to some background, and you can have, but these come in very controlled counterterms that can appear. They take a simple form, and in the end, scheme dependence amounts to an overall factor, and in particular to a choice of these 2 values of U0 and V0 that multiply the area and the Euler characteristic of your surface. Okay. Now, if you follow this approach, you find something that might be a bit puzzling, because you see that the perturbative expansion truncates. After a certain power in the coupling, you find that all the contributions that you get from Feynman diagram, they add up to 0 at each order. But we know that the partition function is not a polynomial because we've seen it in the previous slide. So what is going on is that we are only looking at a perturbative sector of the theory. But we know that we have also instanton contributions. And instanton contributions, you should take them into account, and you can study then a perturbative expansion around not just the vacuum sector of the theory, but also around these instanton profiles that are just the saddle points of your action, the Mills action, and they carry a weight that is this exponential, where at the exponent you have the classical action evaluated on a certain instanton profile. And these are unstable instantons. They're not necessarily minima or local minima of the action. They can just be critical points. And they are labeled by a magnetic charge that takes value in the Courant lattice of your gauge group, modulo the action of the byte group. Okay, but this is already a different way of formulating the theory. Instead of summing over representation, we have a trans series. So a series where you sum over instanton sectors, and each instanton sector carries a perturbative expansion in the gauge coupling. And the third formulation has to do with non-abelian localization. This is something that was introduced by Witten in this paper in the early 90s, and it's a generalization of the Duisterman-Heckman formula that was introduced in the context of symplectic geometry. So I'm going to skip a lot of details, but just to give you a flavor of what's going on. So if you consider a symplectic manifold, M, where omega is the symplectic form, and you have a Lie group G that acts symplectically on this manifold, and the momentum map we denote it by mu. So consider an integral of this form. You have two integrals. One is an integration over the Lie group, the Lie algebra of the group G, and contains this exponential factor where you have some real positive epsilon that ensure convergence of this integral. And then you integrate over the symplectic manifold M, where at the exponent you have the symplectic form plus a term that serves the purpose of making the whole thing equivariantly closed. This is the equivariant extension of the symplectic form omega under the action of the Lie group. So you can show by running a usual argument which is to deform the integral by the action of some exact form and then studying it in a limit in which becomes a loop exact and so on and so forth. But you can show that this localizes on the critical points of the function I, which corresponds to mu squared, where again mu is the momentum map. And there's a contribution that comes from an absolute minimum. You always have this absolute minimum because mu squared is positive semi-definite. So when mu is 0, you have a contribution. And that involves taking an integral over the symplectic reduction of M by G, which means simply taking all the points in your manifold that are associated with a vanishing of the momentum map quotient by G. And if you take epsilon to 0, this reduces to just the symplectic volume of the symplectic quotient. But you also have contribution from higher critical points, because you might have other critical points of this I function here. And they carry an overall weight that takes this form, where you have e to the minus the value of I on the critical point divided by 2 epsilon. All right, so why is this relevant? Because of something that has to do with the gauge, the space of gauge connections in 2 dimensions. So we know that gauge connections on some principal G bundle, they form an affine space. So a gauge connection is not a global one form, but the difference between 2 gauge connection is a global one form. So we can consider the tangent space to the space of gauge connections at a specific point as the set of one form that takes value in the Lie algebra of your gauge group. And it was shown by Atiyah and Bott in these very influential papers in the early 80s that A has a Kähler structure. So you can define this non-degenerate 2 form, omega, and it's Kähler in the sense that you also have an almost complex structure and an inner product that they form this compatible triplet. Of course, if you have a space of gauge connections, you know that you have gauge transformations that act on gauge connections, and you would expect them to act symplectically, and in fact that's the case. And the Lie algebra of the group Cal-G of gauge transformations are simply smooth maps from your base manifold to the Lie algebra G. And the momentum map is essentially F, the curvature. The momentum map evaluated at a point A of Cal A is simply given by this expression when acting on an element of Lie G. All right, and the moduli space of flat connection is precisely the symplectic quotient that I was telling you in the previous slide. Okay, in particular, this is simply the set of connections A that have vanishing curvature F, quotiented by gauge transformation. And we know that this has to do with homologies over non-trivial cycles of sigma. Okay, all this just to apply it to a supersymmetric infinite dimensional version of the formula that we saw in the previous slide. The integral takes exactly the same form, but now it's extended to the supersymmetric version. And the reason why this is interesting is because this is nothing but the path integral of Yang-Mills theory in 2 dimensions in the BF, in supersymmetric BF formulation. And if the story goes in the same way that we've seen earlier, well, okay, this is the path integral. And moreover, sorry, I forgot to say that this function I that I was telling you earlier, which is just mu squared, now is just the Yang-Mills action. So again, if this goes as we were saying, what you're localizing on is that you're localizing on the critical points of the Yang-Mills action. So as in the perturbative formulation, what you find is that your result should take the form of a sum over the critical points, or in other words, that what you're actually doing is that the partition function localizes on the moduli space of solutions on the Yang-Mills equation, moduli space of instantons that are labeled by the magnetic charge. So schematically, you can write it as sum over, well, you're labeling the connected components of this moduli space by summing over the magnetic charge. And each term of the sum, of course, it depends on M and depends on the gauge coupling. So in the paper, in this paper by Witten in 93, the localization argument is used to infer the structure of the result that should come as this sum that I was telling you. But the paper mainly deals with the absolute minimum. And because this has a geometric interpretation, because if you're studying this contribution from the absolute minimum, which is basically involves an integral over the moduli space of flat connections, this is shown to reproduce the intersection numbers of this moduli space. But of course, the full result contains not just the case where M is 0, but contains all the contributions. And as we expect from a perturbative argument, of course, they should scale with this exponential in front. And these contributions in the literature, they only appeared for 2 specific cases, which is genus 0 and genus 1. And very little is known about a generic instanton sector on a generic topology, which is kind of surprising because we have a formulation of the theory, which is, okay, you can compute the exact partition function and compute observables, but it's given in that combinatorial way. And then we have a more like something that contains a lot of physical information, which is either from a perturbative perspective or even from a geometric perspective, where you could isolate the contribution of each connected component of the moduli space of instantons, but the individual component of that sum, the individual term in that sum is just not known in general. So the idea is to try and compute that information. And we have 3 ways that one could see. One is simply to start from the Migdal version of the partition function. And you say, okay, maybe we can take that and we can project it in a basis in which we can isolate the contribution of each instanton sector. The second strategy would be to compute the full perturbative expansion about an arbitrary instanton, but this would involve computing an infinite number of Feynman diagrams on an arbitrary surface, so that probably seems like the more masochistic approach. And the third one would be to apply localization, like a bona fide localization computation that should tell you what is the contribution of a single instanton sector. And we're not going to do point 2, but we want to proceed with both point 1 and 3, and of course in doing so we will deduce what the result of applying 2 would be in the process. Right, so I'm going to discuss a rank 1 example to keep things simple, and we can start from the Migdal form of the partition function. So SU2 representation are labeled by this single positive integer L. So Migdal tells us that this is the result that you get from computing the partition function with the lattice approach. The question is, can we recast this expression here in an expression of this form here, where I have a sum over these instanton sectors, and I know that in the end should look like something like this. This is the action evaluated on the instanton sector labeled by the magnetic charge M. Okay, so how to do it? There's an obvious way on how to do it, which is to use Poisson summation. So it helps us the fact that this function is even, so we can just double the domain and consider a sum that runs over all integers. We have to exclude the point in the origin, but that's fine, there's just one term that we can eliminate. And then the sum over L, which is the one given by Migdal, should correspond just to a sum of where the argument of the sum is the Fourier transform of M. That's fine, and that has been done, as I said, for genus 0 and genus 1, and that's what you get. So here you can see something that I was telling you earlier, that the perturbative, so the vacuum sector has a perturbative expansion that truncates. Genus 0, you have just one monomial. Genus 1, just have these two monomials here. But then you have, yes. So, well, there's nothing necessarily that tells you that that's the case, but you have an infinite sum and you have to recast it in another infinite sum. And you notice here that you have an exponential where at the exponent you have epsilon in the numerator. And you know that evaluating the action on the instanton profile, you should get something that is non-analytic in epsilon. So epsilon is a denominator. This looks very much like a Fourier transform, so you would guess that maybe that's Poisson summation that does the job, and you find precisely the form of the result that you should expect. This is a sum over all the instanton sectors, and namely e to the minus s evaluated on the instanton profile. Okay, so this is the result for, and also it's quite interesting that every instanton sector has a perturbative expansion that also truncates. Okay, so we like this. Why not applying the same to genus 2, genus 3, and so on? Well, the problem is quite obvious, because when the Euler characteristic becomes negative, you have a function now that has a divergence in the origin, and the Fourier transform does not exist in the sense. Okay, fine, but maybe we can regulate it somehow. For instance, you could regard f as a tempered distribution, and maybe you can, there's a sense in which you can associate a Fourier transform to a tempered distribution, and that's what you want to do. However, because you have a divergence in the origin, now by means of a Fourier transform, this is spread everywhere. And so what you have as a result is something that is not summable or not integrable. But that's fine. We know that the result should diverge because we are including the point in 0. We have to remove the point in 0. And the point in 0 is just the integral of the Fourier transform across the whole domain. So the guess is the following. If I want to remove the singular point, which is what I want to do, maybe I can compute the sum of the Fourier transform minus the integral of the Fourier transform. I introduce a cutoff. I compute it. I take the difference between the two, and then I send the cutoff to infinity. However, this doesn't work. And it doesn't work because, yes, the leading divergence in lambda cancels, but you have subleading divergences that are still there. And in fact, this is not a limit. As a C here, and it stands for Cesaro limit. So there's a mathematical literature that's been developed over the last 20 years in the context of the theory of distributions and so on, that deal with this sort of, sometimes they refer to as singular Euler-Maclaurin expansions. So I'm not gonna get into the detail of how to perform this computation, nor what's the definition of this limit, also because from the computational perspective, the definition of the limit is not really useful. It's more about the existence of the limit rather than a prescription on how to compute it. So let me tell you that if you put some work into it and extract this result, what you get is the following. So for SU2, this is what you get. You get for the 0 instanton sector, this is the perturbative part. And again, this is just a finite sum because we know that the perturbative part truncates. This is what you get. But this already appeared in the paper by Witten and has to do with intersection number of the moduli space of flat connections. But the novel part is the following. This is the contribution for a generic instanton, M, and for a generic genus, G. So here you don't see the genus appearing simply because this is written as, okay, an exponential times P, which is polynomially in M and the square root of epsilon, plus another contribution that contains another polynomial Q. And the polynomials are written, if I have to write them in the most compact form that I can, this is what you get. So we expect an overall exponential factor here of this form. And indeed, this is also the asymptotic behavior of this expression in square brackets. So this also matches the idea that we have to have a specific asymptotic behavior of the result. Okay, so this is the result. Extract, yes? Well, in this form, no. No, you don't get it. Where is it? Sorry. Sorry. This is a generalized Laguerre polynomial. Generalized Laguerre polynomial. So generalized in the sense that you also have this variable here at the top. You can also rewrite this in terms of Hermite polynomials, but that would involve complex Hermite in a way that in the end it just it becomes a real expression. But anyway, this is it. And this is also can be written as a sum of Hermite polynomials, but this is the most compact way that you can write this. And you see that here you have a dependence on the topology everywhere. Okay. So this is the result that, for instance, you would expect from localization. But this is also what you would expect from a perturbative computation, if not for the fact that this does not really take the form of a trans-series. So we would like to perform an asymptotic expansion of this term, and that we can do. First of all, of course, this function is not analytical at epsilon equals 0, and that's not surprising. We know that Dyson told us that this is what happens already a long time ago. And we can perform an asymptotic expansion, and we can write it in this form. And this takes a nice compact form. This is an exact asymptotic expansion all the way up to k equal infinity. We have the expected exponential factor, and we have this infinite sum that it's an asymptotic series because the coefficient scales factorially. So if you started from a Feynman diagram expansion, this is what you would get, and you would try to resum this to go back to the expression that we had here. Sorry, that we had here. Anyway, maybe there's some commentary resurgence that I can skip. And for the last part, I want to talk about localization. So we have the result. We could also match a putative perturbative expansion. Can we obtain this through localization? Now, all right, so everyone here knows what localization is, so, but in 140 characters, the idea is that you can study some protected sector through some effective action that describes that is defined on some bosonic moduli of your theory. So instead of doing the standard perturbative approach, you study the theory at one loop in this coupling T that has to do with some deformation of your action. The result is not the original theory, but if the localizing term is Q exact, the protected sector does not depend on T. So that's the power of the localization argument. So before actually performing the explicit localization computation, let's see what our result should look like. So we know that the bosonic moduli will be given by solutions of the Yang-Mills equation, but also the supersymmetry algebra that I showed you in the first slide suggests that the bosonic moduli is also spanned by these solutions here. So we are looking at constant profiles for the auxiliary scalar that live in the Cartan subalgebra of the gauge group. So let's go back to the SU2 example. And so these are the solutions of the equations that we're looking at. And phi naught is this constant mode. So if we lock the value of m, so we look at a single instanton, the contribution should be given by an integral over this constant mode for phi, where we have e to the minus, and this is the bosonic part of the action, of the supersymmetric BF action, evaluated on this bosonic moduli. And then we have the hard part, which is the so-called one-loop determinant, which captures quadratic fluctuations about this saddle. So the goal is to compute this quantity, but this is there is a literature about this because, for instance, there is a result by Blau and Thompson already in the early 90s where they sort of computed this. And this gives this monomial. And this is also pretty much the result that you get when you study the same problem, but in a more general context by doing localization for twisted n equals 2,2 theories in 2 dimensions. And if you consider just a pure gauge multiplet with some twisted superpotential, this should also land on specifically on 2D Yang-Mills. And the result is more or less always the same, that you get this form of a one-loop determinant. However, this cannot be the right answer simply because you cannot integrate this quantity. And yet, morally, it must be the right answer because people propose this, and what they say is, well, forget about the integral for a second, perform the sum first. If you perform the sum first, okay, you see now that for some reason delta does not depend on m, so the only thing that you're summing is this complex exponential. Let's assume that this is a Dirac comb. And now this integral over phi becomes a sum over phi, and you just landed back on the Migdal formulation, where this is the dimension of the representation raised to the Euler characteristic, and you have this e to the minus epsilon L squared at the numerator. But that's exactly what we don't want. We want to extract the contribution of every connected component of the moduli space of instantons. So, and also we want something that makes sense also when you forget for a moment about summing over M. You just want to compute this individual contribution by integrating over this bosonic moduli. Okay, so in a very trying to reduce the localization computation in just a few basic steps, this is what we do. This is the localizing term that we add to the action, which is some Q-exact term. As always, we are expanding about this bosonic moduli, and the fluctuations are scaled by t in the usual way, in such a way that the leading part does not depend on t, and the part which are not quadratic, they are suppressed when t goes to infinity. This is the bosonic part. Is the quadratic expression, and the fluctuations are this tilde. So we have to integrate over a tilde and phi tilde. Now, because phi appears in this way, it's very tempting to just to integrate it out, and that's what we're doing. And in the process of integrating it out, we are producing a functional delta that localizes the functional integral over the kernel of the covariant Laplacian. And if you follow a TM bot, you know that there's a certain number of harmonic modes that survive. They're given by this expression. So again, we are looking at the SU2. We plug in the specific form of this quadratic expression A. And okay, skipping some steps, but we land on an integral of this type. And in an integral of this type, you somehow, with a change of variables, you realize that this is nothing but a certain derivative of the Fourier transform of the Heaviside step function. So in the end, you end up writing something like this. So again, when you compute this functional determinant, you see that in a strict sense, what you have makes sense as a distribution, not just as a meromorphic function. The fermionic part is even more complicated. So I'm just going to mention the fact that a completely analogous term arises from integrating by a certain number of fermionic modes, and the number of fermionic modes is given by this particular expression. And what's nice and what allows you to perform the computation for a generic genus G is that there's an index theorem, which is basically applying the Riemann-Roch theorem, that tells you what the difference between this number of bosonic modes and fermionic modes. That is simply a multiple of the Euler characteristic. So if you combine both the bosonic contribution and the fermionic contribution, you find what is the correct result for the one-loop determinant, which, first of all, as we said, it is a distribution. It has to be understood in terms of a distribution to get a sensible answer. But also, well, but in a way you see that morally it is similar to what was obtained earlier, because if you forget about this delta, and if you forget about this principal value, by taking a certain number of derivatives of 1 over phi naught, you find precisely the power in phi naught that we had at the beginning. But this has the added benefit that you can simply plug this into the integral, into this integral, and you get on the nose the result that you predicted from the Migdal formulation. And also you cannot just limit yourself to the partition function. You can also compute protected operators with the same functional determinant. You just insert appropriate functions of the bosonic moduli here. All right. Sorry, discretized part of what? Right, so yes, so for instance, if you consider Wilson loops, you have to add additional characters and basically you would have a Wilson loop which is running at the interface between two plaquettes, essentially, along these edges. So when you're gluing things together, you don't just glue them, but you glue them with a twist, so to speak, which is you're adding this Wilson loop. Interestingly, Wilson loops are not in a category, in a protected sector of the theory. So they can be computed exactly, they can be computed localization. Localization can compute some local observables, like trace of star F, for instance, is a protected observable. And actually, here, by using the machinery we had earlier, we can compute, for instance, the full perturbative expansion of things like correlator or Wilson loops, which are not protected, but nonetheless we can also obtain from this perspective. So before closing, let me comment a bit on the fact that, which I think it's a bit of a novel feature, that a careful analysis leads to a functional determinant that is a distribution, that is better understood in a distributional sense. So, well, this is not the slides. Yes. So the question is that, are distributions inevitable when you perform localization? Well, this is an example in which I think it's fair to say that they are. But more generally, I think that if you, one loop determinants belong to a dual functional space. So if this is a general structure that comes from localization, where you have this exponential part where you evaluate the action on this bosonic moduli, you have a potential insertion here of observables, and then you have the one loop determinant. The one loop determinant, if this function belongs to the Schwarz space of rapidly decreasing function, delta should be something that integrated against this would give you some number. So in a sense, in a more general, if you don't know what localization produces, if you just look at it from this perspective, in a more general sense, delta is a temperate distribution. And this is what we find. And if you're trying to trace back on a computational perspective, the point, or the emergence of this distributional nature, we can do it with a simple example which directly comes from, is inspired from our computation. So say you want to compute this integral. You have a double integral of this function here. Well, all right, okay, so you perform the integral over phi, and this gives you something which is essentially, upon a trivial change of variables, become a Gaussian integral. You perform the Gaussian integral, and you find the result. Okay, this is like calculus 1. Okay, but you can try and do the same. Now simply integrate first over phi. But the integral does not converge because you have something which is purely oscillatory. But you know that you're integrating against phi, so you do have a test function. So you can give meaning to this integral in a distributional sense, which produces precisely the distribution. And at the end, you perform the integral over phi, and you get the correct result. So why do we get distribution? I would argue that distributions are the price that we had to pay as we split the degrees of freedom in the path integral and insisted in integrating them in a certain order. If you just performed an integration, but you're left with the residual integration to do, you're not guaranteed that what you have is a function, even a meromorphic function, but in a more general sense, this could be a distribution. Okay, I'll get to the conclusions. So the conclusion is that the exact all-order perturbation theory of two-dimensional Yang-Mills is calculable. You don't have to compute an infinite number of Feynman diagrams. You can extract it from the Migdal representation. No, there is no check. So if you have faith that the Migdal representation is also the same result that you get from a continuum theory, that should reproduce the perturbation. Right, so if you believe that, so by perturbation theory, I mean the trans series that you get by summing over instanton sectors and Feynman diagrams which correspond to expanding around that instanton sector. So that's the perturbation series. If the lattice formulation, if you believe that the lattice formulation leads to the same result, you can use the Migdal formula and you extract it. And there are results in which the two things, the people try to match the two things, but the result that I'm aware of was done by Kevin Guyen in 2016, and he computed a genus Z, just a perturbative sector at genus 0. I'm sure that in the literature you can also find other examples, but nothing that is in any instanton sector at any genus that doesn't exist. I think that is really a tough problem to attack. But also the same result can be obtained through localization in the way that I outlined in the last few slides. And what's interesting is that the one loop determinants that arise are necessarily distributional in nature. For G greater than 2, the perturbative expansion about SU2 instantons is asymptotic. And now some outlook. So I presented results for SU2, and that's what you get in the paper. But we have results for other groups like SO3, and we are in the process of computing U2. So this procedure can be generalized. And also to observables. We have the results for homological Wilson loops and correlators of Wilson loop wrapping non-trivial cycles. In fact, this technique can apply, as I was saying, to non-protective observables, and Wilson loops are an example of non-protective observables. So you can go beyond what you can get with localization. But I think that also the lesson that we learned from this computation, and that perhaps is something that can also be applied to other examples on maybe in higher dimension, is that from localization, it's not a novelty that you end up with one loop determinants that might have some singular points, and there are various prescriptions on how to deal with the singular points. Namely, one prominent one is the Jeffrey-Kieran residue prescription. Perhaps there's a way of understanding this from the point of view of distribution theory. And maybe this can also kind of give you a largest set of problems that you can attack in this way. So it would be nice to understand, for instance, the Jeffrey-Kieran prescription from a distributional perspective. And of course, in the context of two-dimensional gauge theories, there are obvious generalization, non-simply connected groups, discrete theta angles. You can insert vortex operators and also consider manifold with boundaries. All things that can be surely dealt with by studying the Migdal representation. All right, that's it. Thank you very much. Yes. I think from the perspective of an equivalent of the Migdal formula, I think it should be fairly straightforward. That's what I would expect, although I haven't attempted that, so I cannot comment for sure, but I would expect this to be doable, yes. Yes. Sure. Right. Yeah. Right. Yeah. Right. Yeah, yeah, yeah. So the answer is that I'm not sure. um, and well, yeah, I'm not sure if that's it sounds reasonable, and maybe even someone from the audience has some comment about this. I'm not sure where I can interpret this. That surely this the results that were obtained for in the supersymmetric setting for twisted n equals 2,2 theories by Benini and Zaffaroni. They also have a natural lift to 3 dimensions. It's not clear to me whether you can interpret this dual representation, like either the Migdal or the sum over instanton sectors from this perspective. So that's a good question. I don't know the answer. Sorry. Yes. Yeah. 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 That's right. That's probably relevant to the previous question. Yes. Sure. I don't expect anything else because the match between the Migdal and this trans series is exact. So there's nothing left. So either the Migdal formula is wrong, or that's the trans series is all you get. Right. Yeah. Um, so in principle, I don't have an argument to tell you that the trans series that I wrote down, it's the end of the story, other than to say that the other two ways to formulate the theory, which is the lattice and also the localization one, they point out that you should really have a sum on those contributions. Like from the Migdal, you just get it through that generalized Poisson summation, but also localization gives you that bosonic moduli. You're summing over those critical points of the action. And there are no other critical points of the action. So I think it's probably a feature of 2 dimension that is simple enough that you don't get other weird contributions. So you mean that if I looking for critical points of the Yamil's action, uh, right? Ah, sorry, real value. Yes, yeah, yeah. So this involves, yeah. So the question of a choice of contour is actually an interesting point. In fact, I was mentioning that the work of Benini and Zaffaroni connects with this, but only up to a certain point because they have a different integration contour for the complex scalar. So yes, in this formulation, the degrees of freedom are real, but other formulations can use different integration contour, and it would be interesting actually in trying to match this different um, prescription and reality condition on your fields. Although in the end, the result for the one-loop determinant always take that form. If you look at the literature, both for the paper of Blau and Thompson, and also for these more recent papers, in the end, even ignoring just the reality condition, you have that just monomial with a negative power in phi naught. So I would expect that there are not many ways to deal with that other than to generalize the distribution the way I did. Sure. Yes. Yeah, absolutely. In fact, if you start from, like, go back to the very first slide. So here you have this BF action. And the BF action contains that quadratic potential for phi. Of course, nothing prevents you from introducing other invariant polynomials that you can construct out of your Lie algebra. And that would simply modify the Migdal formula by having not just a quadratic Casimir, but some combination of other Casimirs there. And this is just, it gives rise to all sorts of generalization of Yang-Mills. So in principle, the same techniques can be applied to, in fact, there was a question earlier about also another, which is a Q deformation, which is another way of deforming it. There are various things that you can do here. Well, definitely. So the machinery that we used, for instance, to move from this formulation to the formulation in terms of instanton sectors should just apply straight. It might be more complicated to extract results, but the idea should be the same. Right. Uh, so I don't have a very good intuition about this. I was so. No, so yeah, what I was saying is that I don't have in fact, the statement that I'm making is that I have an example. And of course, this example is telling us something, and I would like to understand a bit better what this is telling us. One of my collaborators, Itamar, he has, I'm trying to convey his opinion as accurately as I can, but you probably should ask him. He thinks that this has to do with some modes that fail to be massive. And that's where you get this. Sorry? Yeah, in a way, yes, but right. Yes, it has to do with massless modes. And these lead to this non-integrable, well, that leads to this distributional perspective. But we really are, this is something that we're actively thinking about, because we're trying to extend this to indices in 3 dimensions and other type of localization computation. This, while we were doing this, we realized that this might be just a toy model for something a bit more complicated than this theory. At the moment, I don't have a definite intuition for this.